Hello, everyone, and thanks for being here. I'm surprised that there is actually people because there are very interesting talks in the main stage and side stage. So today I'm here to talk a bit about folding schemes and Sonobe. The idea is to first give a bit of motivation and introduction to the ideas of folding schemes and the building blocks to build the IBC and how to end up verifying this stuff. And then to talk a bit about the Sonobe library, a bit of benchmarks and the main idea behind it and so on. So first of all, as a bit of motivation, we are in this snark ecosystem, snark world, where we care about proving computation and sometimes hiding stuff. Usually, the way how we do these snark programs is that we want to be able to prove this set of constraints that we define as this program with some ZK language. And the idea is that we want to prove this as a set of constraints that we encode as polynomials. As a simple example, like this R1CS, rank 1 constraint system, we have these matrix vector operations that we kind of translate into some polynomials with the QAP. And then once we have this in the shape of polynomials, then we can use a variety of tricks in the cryptography realm so that we can prove the relation of those polynomials with some witnesses that satisfy the relation and so on. For example, Grok 16, Marlin, Spartan, whatever. So those are examples of different ZK snark schemes that allow us to prove these polynomial relations. TLDR, we want to prove polynomial relations. So just to have this first insight towards the folding ideas. Then why folding? The idea is that when you have some kind of shape in your computation that you want to prove in those snark programs that require some repetitive computations, these end up taking big circuits, which translates into large proving time. And in some cases, also, it takes too much memory and cannot even be computed. Or if you have some limitation in terms of the device that you are using to prove this stuff, it might take too much memory. For example, if you want to prove a hash chain of 10,000 SHA-256 hashes, I hash this input, and then the output I hash it again, and the output I hash it again, and so on, 10,100K iterations of this. This ends up taking too much constraints in the R1CS example. And with most traditional snarks, if this grows enough, this takes too many constraints, and it's not feasible in those cases. Also, if you want to prove, for example, the ZKVM, you need to do some extra acrobatics because and also the thing is that the opcode, you are iteratively proving the same opcodes again and again and again. So the same set of constraints that you are proving again and again and again. So one way to kind of cover this is with traditional recursion, or how Justin Thaler calls it, brute force recursion. So the idea is that we verify inside a circuit the proof of the same circuit being proved in a previous iteration. So here you have this will be the circuit layout, and you have the part of it is verifying the new instance data. In this case, it's just verifying a signature, or could be computing the hash or whatever. And then also you have part of the circuit that is verifying the proof. In this case, Grok 16. The issue with this is that the verify a Grok 16 proof within a circuit of Grok 16 with R1CS ends up being a bit expensive, some millions of constraints. So that's a bit of the motivation on why we are interested into folding. We use folding, but we use it in this context of IBC, but also sometimes with PCT, proof of carrying data. Here, the IBC stands for Incremental Verifiable Computation, comes from a paper from the 2008 from Valiant. And the idea is that we can prove that applying n times some function f, which will be the circuit that we want to prove, we apply n times this function f to some initial state. After n iterations, we obtain this final state. So that's kind of the mental model of the IBC. And this is the kind of simplified view of this, where it's basically you compute f applied to some z0 initial state with some extra witness. And then to the output of this, you apply f again, and you apply f again, blah, 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 etc., until you have applied this n times, and then you obtain some state. And you put this together with some proof that proves that, this relation holds after these n iterations, which could be this hash thing. Then this diagram will be appearing many times, well, three more times during the slides, just to have the context where we are at each moment of the slides. So the folding schemes pipeline, or kind of anatomy, the idea is that you have the circuit that you want to fold. You kind of input this as through some front-end interface. This is what gets you from the ZK language defined circuit to some arithmetization. Then we wrap this circuit into kind of like an augmented circuit, this wrapper for the folding. And then this is fold through the IBC shape of doing things n times. And after these n times, we actually compress the IBC proof through the decider. This is in the high level. Now we are going to dive in each of those parts. So first of all, a bit of recap on folding. I will focus into the Nova folding because it's like kind of the simple one to explain now. But we'll give a bit of intuition also in HyperNova and ProtoGalaxy. So the idea with folding is that, as we said at the beginning, we care about like proving polynomial relations. So one thing that Nova proposed is that usually you prove the polynomial relation, but also you use some tricks. So you commit to the polynomial, and then you work also with you need to deal with the commitment to the polynomial. So here we use additively homomorphic commitments. And the idea is that in this example is like using Pedersen, but you could use KGG commitments or stuff like this. And the idea is that if you do a random linear combination of the polynomial, and on the same time you do the same random linear combination, so V and W, they are two original polynomials. And then this R is just a random value, some challenge. And then you basically do a random linear combination. It's like V plus the W multiplied by R. And then you obtain this Y polynomial. If we do this in the polynomial or in a vector, and on the same time we do the same operation but with the commitments to this vector or to this polynomial, the obtained polynomial or vector and the obtained commitment will still hold the relation of commitment between them. So doing this operation in one side and then just doing the commitment to the Y obtained here will result also into getting the commitment of Y. This is like the kind of the key idea of this random linear combination, which is Nova and some other folding schemes based on that. This is the idea. Then if we try to apply this to R1CS instance, because in our case we care about like folding those polynomial relations, it could be R1CS, it could be Plonkish arithmetization, CCS, stuff like this. If we try to do this, we will not go now into the details, but like you end up having some inequality with the plain original R1CS. So the solution that Nova proposed was to relax the R1CS. So instead of like the typical R1CS relation, we work with this relaxed R1CS. Basically, the main difference is that we add this U term. It's like a scalar. And then this is like a vector of scalars, this E, which is the error term or slack term, depending on the paper. And then we have the witness instance, which now it's not only the witness, but also the error terms, this vector. And then we have the committed instance, which contains the public inputs, this new U parameter, and then the commitments to W and the commitments to E. So this is like what we deal with in Nova. Very recommended in the Nova paper in pages 13 to 15. This is explained very well with like first attempt, second attempt, third attempt. And so the paper guides you through the logic of why we do this, the thing in this way. So then once we have this relaxed R1CS relation, and we have this idea of random linear combinations, we can put things together and we can build this kind of protocol where the prover and the verifier interact in a way that later we transform through the Fiat-Shamir heuristic into a non-interactive protocol. But the idea is that they both will fold those instances that we have for a valid witnesses for the R1CS that we are checking. They will both fold, like random linear combine those things in a way that the verifier and the prover will obtain the folded committed instance, like the commitments folded from the two original instances, while the prover also obtains the witness to this folded committed instance, so the folded witness. So the idea here is that both will start from two valid instances and, well, two valid committed instances. The prover also will have two valid witnesses for those respectively committed instances. And then both will end up computing those random linear combinations. This is very simple math. It's just like doing additions and multiplications of vectors, of elliptic curve points, or just scalars. And then the obtained folded, like random linearized instances will still hold both the relaxer1cs relation and the commitments relation. The idea here is that we are kind of like reducing from two instances to a single one. So that's kind of like the power of folding. So at the end, we need only to generate like a snark proof for one instance instead of the two original instances. And if you do this n times, so you are kind of like accumulating or aggregating those n different instances. So the issue with R1CS is that when you try to do this with more than more than two instances, if we try to fold 10 instances, the issue is that here there are some cross terms, like this t parameter, well, in some of the places, here, up. And the thing is that this will grow like linearly as more instances we try to fold. Like when you try to do the math of the random linear combinations. So this does not scale well, but then some papers appear later, like HyperNova, ProtoGalaxy, and so on, which provide solutions to be able to fold multiple instances. So before we were talking about NIFs, like non-interactive folding scheme. Now we talk about NIMFs, which has this M, which stands for the multiple instances. So non-interactive multifolding scheme. The idea here is that in HyperNova, we use some sum check tricks and so on with multilinear extensions and the Boolean hypercube and so on. And ProtoGalaxy uses the Lagrange basis, but also has a variant in the paper explained where they say if you have more than k instances to be folded, it might be worth also to use sum check and multilinear extensions. So basically, the idea is that with those papers, it allows you to fold more than two instances per folding step. Just a bit of like visual idea on how this looks. This is like in the HyperNova. The first one is like 2-to-1 folding. So we are folding, we have the running instance and then the incoming instance. We just fold them, and then we obtain a new running instance. And then we will fold this again with a new incoming instance, and we will obtain a new running instance. And we keep doing this on and on. This is 2-to-1. Then HyperNova allows us to do this k-to-1 fold, where we have still the running instance, but then the incoming instance, you can have a bunch of them. So you can have like 10 or whatever. And you keep folding them. So per each folding step, you are kind of like folding more stuff. So in the same way that we were saying that in Nova, the folding scheme is based on just doing random linear combinations. So it's just like you take this scalar and you add it to the multiplication of the other scalar multiplied by R, and you obtain the new thing. And all this thing applied to all the parameters of the instances, you obtain the new folded instance that is basically like a random linear combined from the two previous instances. In HyperNova, we use different tricks. Also, we use random linear combinations, but also we use sum check to provide like a better consistency on some things, which ends up allowing us, also using the multilinear setting and so on, allows us to have this like multi-folding, that we can fold multiple instances per step. This is a screenshot from the paper. And in ProtoGalaxy, also different tricks. So HyperNova and ProtoGalaxy are a bit more complex than the Nova way of folding, but at the end is like building blocks that we have also on other snarks. In fact, HyperNova, the tricks that is doing here is similar to the Spartan ideas, which makes sense because the authors are like almost the same. So yeah, so recall that this is the diagram that we already saw. We have this folding schemes pipeline. What we've seen now, these folding schemes that we do the random linear combination or the sum check, depending on the folding scheme, the idea is that we don't run this as an interactive protocol. We run this as this non-interactive through the Fiat-Shamir heuristic. And in fact, the verifier of this protocol, we encode it inside a ZK circuit, which will be actually the circuit that we actually fold. So it's a bit of like inception, but the idea is pretty simple. It's like we want to ensure that when we fold the things, the folding itself is well computed. So the way is like, since we are folding already some circuit, we will encode the NIFs verify, like the folding scheme verification, which in the Nova case is just doing these random linear combinations. We will do this also inside the circuit in a way that we, in the circuit, we are enforcing that those operations are well done. And also, so we have, this is the circuit that we want to fold, this F circuit. So we wrap it in this augmented F circuit, is this wrapper. This is the folding scheme, actually, the folding circuit that actually we will fold, which contains the original circuit, the F circuit, the NIFs verification, which in the Nova case is just doing random linear combinations. In the case of HyperNova is doing sum check and some other stuff. In ProtoGalaxy is dealing with the Lagrange basis. Instead of random linear combination, we do the linear combination using the Lagrange basis, or sum check, depending on the variant of the ProtoGalaxy. And then also we need to run some hash checks and some other checks. So kind of we wrap the F circuit into this augmented F circuit, adding these other like checks. That's the main idea. So now we have the folding scheme. How do we ensure that, or how do we build up an IBC layout from just the folding scheme? So we need to ensure that each folding step, the NIFs is correctly done. We do this through this NIFs verify. Also, the main idea is this, and we need to run also some other hashes and so on. So in the case of Nova, this is doing this packet here, NIFs verify. This is doing scalar field operations, which are native in the circuit where we are working. And also this means doing group operations from the elliptic curves, which is point operations. In HyperNova, we also have this, plus the sum check verifier, which also contains, like, the expensive part is like the hashing that you need for the transcript of the sum check. And then in ProtoGalaxy is like also similar, but also with the Lagrange bases involved and so on. The issue here is that we need to run this circuit over the first curve, and this NIFs verify needs to do the random linear combination of some points of this elliptic curve 1. The issue here is that the elliptic curve operations involve doing operations of the coordinates of the point, which those are over the base field of the curve, of the group. And here, the circuit, we are dealing over the scalar field of the elliptic curve. So then this is what we call the non-native or wrong field arithmetic or different names. But it's like the non-native arithmetic. So doing non-native arithmetic inside the circuit of Snark is very expensive. So what Nova proposed is that they will mirror the entire circuit, this wrapper circuit of the folding. They mirror it into a secondary curve, like fully duplicating the entire thing here. And then this circuit inside will be doing the whole checks and folding and so on, but this will be computing natively the point operations of the circuit on the first curve. And then the circuit in the first curve will be like checking the point operations of the secondary circuit in the second curve. This is fully duplicating. A couple of, or 1 year and something later, CycleFold appeared. And CycleFold is, so just so you can appreciate the difference, is almost the same, but we are reducing from duplicating, like mirroring the full circuit, into just having this like smaller circuit where we just do the specific computation. And yeah, but that's, I mean, some details, but that's the main idea. And in Sonobe, we implemented CycleFold, and we use it for the 3 other schemes that we have, like the Nova, HyperNova, and ProtoGalaxy. We are relying on the CycleFold ideas. This is actually how the circuit looks like in Nova. So the circuit, just to provide you a bit of like intuition on what's going on, this F here is the circuit that we want to fold. This is the actual circuit that, as a developer, I want to fold this circuit that verifies signatures or hashes or whatever. This is the F here. Then the NIFs verification, this random linear combination or other stuff, is this one, this box. And the rest of things are just extra checks, extra hashes. This is doing the NIFs verification of the CycleFold circuit. And some extra hashes. So this adds, as you can imagine, this adds some extra overhead on the folding. So if I want to fold a circuit that has 100,000 constraints, this F circuit has 100,000, once we wrap it in this rapid folding circuit, this augmented F circuit, this adds an extra of, in this unoptimized case, it takes about 50,000 constraints. So this would end up being 150,000 constraints. So it's one thing that we take into account when we do the folding. And the full diagram is in the Sonobe documentation. Then, OK, so we are here. We just seen the IBC. Now we are going to see this final stage of the decider. So the thing is that we keep folding using CycleFold and keep moving between curves. And at the end, we end up having 3 instances, which these are the witnesses, but also the commitments to the instances that we end up having folded after n iterations. So if those satisfy the relation of the relaxer1cs and the commitment relation, this means that all the previous folded instances that we've been folding at each folding step, they were also satisfying the relaxer1cs relation and the commitments. So the thing here is that those are quite big, like some megabytes of data. So the idea is to compress them through a final ZK snark proof. Those are the checks that we need to do in this decider. The decider, the name comes from some of the papers, and it's like, yeah, it decides whether the IPC proof is correct or not. Another way to refer to it is this compressed snark final proof. So we need to check some folding verification, some extra checks with some hashes, but then the correct relaxer1cs relation and the commitments for this final instance, and the same for the CycleFold instance. The thing here is that this is over the first curve, those are over the second curve. So you can imagine that this brings some issues when we try to converge things into a single snark. So those will be not native, and this will be native, but this is like, if it's Pedersen, this might take like 5 million constraints or so on. So the thing is that in the original Nova, they modify a Spartan to also use the commitment and to prove the commitments inside, and they generate 2 Spartan proofs, one for each of the curves. The thing is that in our case, we were aiming for verifying the folding scheme in Ethereum. And as you know, Ethereum has some limitations or some constraints, restrictions. And so we can, for the moment, we can only use the BN254 curve, which has the pairing. And also we care about like the gas costs. So we needed to do a bit of gymnastics to verify the folding proofs in Ethereum. So those are the checks that we will do in a normal setting, that we could distribute those between different, like the 2 curves, so things are native. This is part of the checks that we do for the on-chain decider. Here you have more details, but it's in the docs. But basically, it's like instead of doing Pedersen commitments on both curves, one of them we do KGG commitments along all the way of the IBC. So at the end, instead of needing to do them non-natively in the circuit, which will be prohibitively, we do them outside of the circuit as KGG directly in Ethereum, which is not so expensive. So yeah, this is the idea. So from this final iteration of the folding, some of the things are proven through some growth 16, and then the commitments, some of the commitments are proven through KGG. So at the end, in the EVM, in Solidity, we verify 2 KGG proofs and 1 growth 16 proof. So okay, so just to wrap up, all this stuff is like, okay, how to use it. So we've been, for this past year, in this joint effort between Xerox Spark, where I'm from Xerox Spark, and PSC, where folks here are in this room also. So this joint effort between Xerox Spark and PSC, we've been building this Sonobe library. Sonobe is a concept from the origami world. So since we are folding, it was a fun word to use. The idea is that we have this library to add and test new folding schemes, because there was this period of time where new schemes were appearing every few months. So it was like, okay, we want to be able to quickly iterate and implement them and reuse part of the code and so on. Compare apples to apples, and also that researchers can easily add their own schemes. For example, the Nethermin research team published this MOVA paper, and for the paper they implemented the MOVA scheme on top of the Nova implementation that we had. So and now they open it a pull request. So now in Sonobe we also have the part of the MOVA implementation. And also, so this is for the research part, but also we were trying to make it easy for devs to use the folding. The idea is that as a developer you just need to care about about the minimum code, like plug and fold. Also, thanks to Arkworks, it's easy to switch between folding schemes and curves. Also supporting multiple circuit languages like Arkworks and Noir, Circom, and Noname. Important remark, everything is very experimental and unoptimized, so just if you use it just for experimental things. The developer experience is just like you define the circuit to be fold. So this was the first part is the pipeline, but this is like the actual experience of the developer. So you define the circuit to be fold, satisfying some interface. You can do this with different ZK languages. Then you give this to the folding engine. You do n iterations of the folding with the ABC, and at the end you can generate the desired proof, which you can choose between generating an on-chain or off-chain proof. The on-chain is for Ethereum, and also the library generates the Solidity verifier that you can deploy, and then you can verify the proofs. So the current status of the library is that we have the schemes implemented, like fully implemented, which includes like you can do the full flow with Nova, HyperNova, and ProtoGalaxy, all of three using CycleFold. And recently we started to add the MOVA and OVA variations of Nova. Those variate the Nova random linear combination, avoiding dealing with in some way with the error terms. So we have this started. The next thing is to add for them like the folding circuit, the ABC, the decider, and all the pieces. And also as front ends, like by default we have Arkworks because it's like the entire library is built on top of Arkworks. But as experimental we have Circom, Noir, and Noname. So just very quick, maybe we don't have time, but we started late. Yeah, okay. But it will be just 30 seconds. So just as an example, so here there is a bit of boilerplate, but the idea is, okay, so here I hope that you see it. We can zoom a bit. So here we define that we want to use as folding scheme. We define that we want to use Nova with some elliptic curves, with KGG commitments, and for the first curve commitments, and then Pedersen commitments for the second curve commitments. If we like to not use KGG because some thing, we can just use the same thing, but here I swap the KGG by Pedersen for the first curve. Or now I say, oh no, you know, I already have all the code working for Nova. I want to try now HyperNova, so I just do this. Or if I say, no, okay, now ProtoGalaxy, the same, and here you define the commitments and so on. There are some combinations that currently are not supported. Like if you want to verify on-chain in Ethereum, the proofs of using without the KGG, this is not possible. But yeah, that's the idea. And then, yeah, so here we initialize the folding. This is the initial state. In this case is doing the typical I equals x power to 3 plus x plus 5. The typical example from the Vitalik blog post from maybe 7 or 6 years ago. This is, so okay, we initialize the folding scheme, and then here we do 3 iterations of the proof step. For 3 iterations, it's not worth, like in terms of like the time that you need and so on, but you will here do, I don't know, 1,000, something like this. But anyway, so you just call this proof step, and this internally, this builds this wrapper folding circuit, and it will fold it using the whatever folding scheme that you choose. In this case, we are with Nova. Then you obtain the IBC proof, and then you can just verify it. Then you will care also that this proof is some megabytes of data. You could still compress it with zip or something like this. But then what you do is you define some decider, which is this final prover. And the same here, thanks to Arkworks modularity, you can just swap it in curves or the commitment scheme. Even here, now we only support Growth 16, but eventually you could put here the Spartan prover if it fits the trait of Arkworks of Snark. And then, yeah, just decider proof and decider verify. And furthermore, if you are using the on-chain decider, you could also here like generate the Solidity code that allows you to verify on-chain. So last slide, because the last one is just links. Some numbers. Again, remark, this is very highly experimental and unoptimized code and just for kind of research. So don't expect to use it in some project that will depend on it. So the current folding step with a small circuit and using the pasta curve, like the Pallas and Vesta, it's around 300 milliseconds. This is amortized as your folding circuit is bigger. So when your folding circuit is very small, since we have this overhead in the wrapper folding circuit, the augmented F circuit, so this in fact is 50K. So if your circuit is 10K, the 50K of the overhead takes most of the percentage of your actual full folding circuit. So you need to design your system in a way that this 50K is a small part of your full folding circuit. Then the off-chain decider proof, this is the current naive implementation is less than 1 minute. But then the thing that was kind of the objective of this project was to be able to verify folding schemes on-chain, because so far there were no options. So this final circuit that we proved to verify on-chain is like around roughly 10 million constraints. It takes like 3 minutes in this ThinkPad. And this is unoptimized. And then the gas costs currently is around 800K of gas. It's basically like 2 KGG proofs and 1 Groth16 proof. And the idea is that you can do some tricks hashing the public inputs, but also batching the pairing check. And ideally, we could be able to reduce it to 500K of gas or less. And again, this is the cost to verify this very, very big kind of like iteration of proofs that you are proving that after applying n times this function f to this initial state, you obtain this final state. So yeah, so that's it. I hope that in the documentation website you can find a bit of more like insights on the ideas. So there are 2 sections. One is like how to use it, and then the other section is about like some design choices that we made, like the circuit or the decider approach and so on. This QR code points you to the repo, and in the repo you have all the links. And yeah, so that will be it. Thank you.